Hello everyone, this is Physics Prism, presenting before you Wave Dynamics Video 1 Modeling String Waves. In our previous video, we have covered projectile motion with air resistance, and now today we are focusing on wave motion. And this is a series of multiple videos that are upcoming on wave dynamics, and today we are particularly looking on the motion of a string wave on an infinitely long string. Okay, so let's get started. Now, let's get started onto the basics. Let's start from the basic and then we move on to complicated things. First things first. Suppose you have this kind of axis and along which you have an oscillatory function, okay, and that is moving, and due to that force your string is performing oscillation. Okay, and this is we will call an oscillator. X equals to 0 at position, and this is our x-axis, this is our y-axis. Nice. Now, how is this oscillatory function defined? We define it as a displacement function y as a function of x and t. This is the displacement function for the particles in the wave, and for the oscillatory function we will see later how we define all those things. Okay, now what we do, we take two considerations. Firstly, that we consider the string is uniformly dense. That is, we can define the density of the string rho to be Lm over L. That is, the mass of the string is uniformly distributed along the string. Okay, and we say T to be the tension in the string. Nice. T is the tension in the string. Now, we define two more things before we go to the FBD of the string. We define two more things. And the first thing that we are going to define is the function, a force function. Okay, what is this force function and why is it useful? So this is actually applied force divided by unit length. Okay, applied force divided by unit length, we are going to define it as f of x comma t. And there's one more thing that we need to define is the resistivity, the resistance or damping force. So we say the damping factor to be beta, and it will be affecting like this. Okay, so this is the thing. Actually, we know from our previous video, we know that resistance is directly proportional to velocity. One minute, it's not working. Why is it so? Resistive force per unit length. Fine. Now let us move on to the FBD of the string. How we make the FBD of a string and to derive the equations from there. So let's zoom in to a very small portion of the string. Suppose this. We can see that there is a tension force in this side, there is a tension force at this side, right, which is making an angle theta with respect to the horizontal. and we get to know that there is a force on this side, and this force is nothing but f dx. Whoa, f dx. What is f? F we have already defined to be applied force per unit length, and we know that there is a damping force, so that is beta del y by del t, right? So this is the thing. Now, since we are talking about an infinitesimally small portion of the string, so we can tell that this portion is dy and this portion is dx, telling that since we are dealing with an infinitesimally small segment, so the slope of the string almost remains the same, and this is dl. So we can say that dl is nothing but uh, root dx squared plus dy squared, right? This is the thing. Remember, we are talking about string movement, right? So dx is greater, much greater than dy. Why? You can make sense out of this, right? This is string. This is how a string motion works. I hope it is clear, and thus see the angle that this makes, uh, this portion of the string makes theta is same as this thing, right? And so theta must be less than 4 degrees, the small angle approximation. We know this fact, right? Now, since theta is much less than 4 degree, so we can say that sine theta is approximately equals to theta, and sine theta plus the theta, that is the change experienced by some this this portion. This is the actual angle, if we call this theta. My apologies to write it wrong. Will approximately be equal to theta plus d theta. These things are to be kept in mind. These are very crucial factors that are uh, controlling our wave motion. Now, let's draw conclusion from here. What we can tell from here, this portion. Okay, what we can tell. See, we know that dx or dy is very small than dx, therefore dl will be approximately equals to dx. Why? Because then dy becomes negligible in terms of dx squared, and since dx squared is under the root, so we get dx, so dl is approximately equals to dx. Now on the next page we are going to apply Newton's laws of motion for all these things, but there is one more thing. Let's talk about the slope. Let's talk about the slope tan theta. Since theta is much less than 4 degrees, so this must also be equals to our theta. And since we know that d theta by tan theta is dy by dx, so we write dy by dx is equals to theta. And thus we conclude that theta over here, since y is a function both of time and displacement x, uh, sorry, in x-axis y depends on the x-axis and y depends on the time factor, so this is a partial differential we can make with respect to x, the slope at instance t, right? Fine then, let's move on to the next page for Newton's laws of motion. Let's apply Newton's laws of motion on the next page. Okay, so are you ready? Changing the page. We are now going to not define, rather derive our wave equation based on Newton's laws of motion. Applying Newton's laws of motion, we know that Newton's second law tells us that our forces in any axis, sum of all the forces in any axis is exactly equals to the mass of the particle times the acceleration in that axis of that particle, right? So if we apply this very thing onto our string, we get to see that the sum of the forces on y direction, that is ftx, minus beta y dot dx, right, plus t sine theta d theta minus t sine theta is equals to rho dx y double dot. Now what is this rho dx? See, we have defined rho to be m over L and dx is approximately equals to dl. So for the small interval of that string, we define our mass to be rho dx, right? This is just a basic manipulation we can play with. We are better playing with. I think the font is becoming a bit small. Let me write bigger for clarity. Okay, so rho dx y double dot. Now why is this double dot? This is the second derivative and single dot represents first derivative, dx minus beta y dot dx. Now look at here, this sine theta plus d theta is approximately equals to what? Theta plus d theta, and this t sine theta term is approximately equals to theta. So we can see that t theta terms will cancel. So the only term that will remain is t d theta, right? And what is this d theta? We say that uh, no, we will come to that. We will come to that. Okay. Uh, now now let's take this dx over there. I mean to say that let's take this thing of the whole function. Okay, if we take a derivative with respect to x, we get rho y double dot is nothing but f minus beta y dot plus t del theta by del x. Now what is theta? That is del y by del x. We have shown it over here. So since this is del y by del x, so our d theta by del x, del theta by del x is nothing but d del 2 y by del x2, right? So we just directly put in there without writing so much and making the scene messy. Okay, now so we have these things. So what about to do rho? We will send the row that side, and we will define some constant which we will which we will be getting help from later on. Let's come up over here. There will be a row. Remember that. Let's define gamma to be beta over rho and c squared to be tension over rho. If we define that, then in our equation of motion, we can change these things, this over rho term and this over rho term, to be our standard things, gamma and c squared. So this is the equation of motion we derive for a one-dimensional string with damping and tension. Now we solve it for what? We solve it for some initial conditions. Let's check. This is In this video, we are not going to go in detail of all kinds of oscillations like forced oscillation, damped oscillations, and this resonance and all that. But here we are just concerned with the general type of oscillation in a string. What do I mean by general? You will just know as I write out the initial conditions, you will get to know what do I mean. So this is the initial conditions. What are the initial conditions? Firstly, we define that there is no external force acting on the string. That is, fx time means x comma t is 0, and at time 0 our displacement will also be 0. That is, the string is just resting on the x-axis. And we say similar thing with the velocity of the particle in the string, that the velocity of the particles in the string must also be 0 at t equals to 0. Okay, now if this is the thing, then what is the boundary condition? Let's define the boundary condition. What are the boundary conditions to be followed? There are two things that we must follow. One is the oscillatory displacement function, and that is x comma t must be equals to some function ft, that is the displacement function. And one more thing, that our string length must be greater than x must be greater than equals to 0, and this is x equals to 0, and at x equals to infinity the string shoots up. Okay, the string is still there, at infinity. And so we define one more thing, that at displacement 0 at any time t our function f is t. Okay, so this is the thing. Now what we do, we now do a legendary thing, and that is nothing but applying Fourier transformation. That is really a legendary thing. So if you don't know a bit of Fourier transform, I'm not going to explain it over here. You can search it in YouTube, it's already available over there. And yeah, I will be linking a video which explains Fourier transform at great depth. So we define a Fourier transform of any function y x comma t as this thing. And there is also Fourier inverse that would give us the actual function from the Fourier space. My stylus is betraying, I can see. Yeah, now it's okay. That would give the actual function. And what is that? That is exactly equals to from negative infinity to infinity y tilted x comma t e to the power I omega t d omega by 2 pi. This is the thing. Okay. In the next page, we will be applying the Fourier transform on our function, existing function, and see what happens to there. So this is Fourier transform application. Let's go. Let's apply Fourier transform. If we do Fourier transform of our existing wave equation, since we know that in Fourier transform, derivatives with respect to time are similar to multiplying with I omega. Therefore, we do the same. We take the second derivative of y tilted plus I omega of y tilted minus c squared del y tilted as a function of this by del x, and this whole thing is nothing but 0. Why is it 0? Because there is no external force. Our f of x comma t function is 0. But why can we find them? We can find them in forced oscillators, not here. Okay, so let it be 0. Now from here I will give you a homework. What is that homework? You will try manipulating this function to get something like this. This is actually the second derivative, means multiplying with I omega, you can understand. Okay, and this is 0. Do this. This is your homework. You will pause the video now, and I tell you to pause it now. Pause it, do it, and if you face any kind of problem, feel free to comment just below the video. Now, coming back, what does this equation tell us? This is nothing but SHM. Oh my god, this is SHM. And it's pretty obvious. So we know what's the general solution of SHM. We know how to solve a general SHM solution. What is that? We have A times e to the qx plus b times e to the minus iq iota qx, right? This is the general solution, where this thing is what? What is this thing? This is nothing but the amplitude of the left moving wave, and this is the amplitude of the right moving wave. So amplitude of the left moving wave, amplitude of left moving wave, and this is amplitude of right moving wave. Okay, I have written in short for your notes. Now, what is q over here? Can anyone tell me? This is our omega in classical SHM. This is classical SHM. Yeah, I mean to say in our day-to-day SHM, simple SHM, whatever you call it. This is just this. This is defined to be this. Okay, fine then. So we get solution? Do we? No, not yet. We have just got a form and we need to improve on this form that we got. So let's keep it for our next season or next video, and we would like to end up over here in this session. In our next part we will talk about just deriving out the equation of motion, and you will get the wave function. Stay tuned on our channel, and if you like this video and want to get the next part and the upcoming videos, then like and subscribe, hit the bell icon and stay tuned. Thank you. Signing off, Physics Prism.